All right. Today we're going to be talking about vectors, and this is first half of chapter 3, and then we're going to go back to chapter 3 again after chapter 2 once this first half is completed. All right. So vectors is a very important thing to know for physics. That's why we're covering this as the beginning of the physics topic. Um, Most likely in universities and colleges, physics, when you're learning physics, vectors going to be the first thing you will talk about. All right. So, what is vectors? Well, a lot of things can be represented as vectors. But for now, we're going to say vectors have two things. It has a magnitude, and it also has direction. So, why is that important? Well, let's say we talk about like a number line when we were like in grade school, right? And I say, oh, this is my house right here, and of course I put my house at the reference point, right? And then I'm going to say, Sally's house is like 2 blocks away from my house. But if I just say 2 blocks away from my house, like you have no idea where Sally's house is because is it 2 blocks north, south, east, west, or northeast? We don't know exactly where that 2 blocks is, right? But if I say, oh, Sally's house is 2 blocks away towards east from my house, then I'm like, oh, then I know exactly where Sally's house is, right? So not only magnitude is important, but direction is important. And vectors have both of these. Okay, so magnitude, what does that mean? Magnitude means a numerical value. It's basically the size, right? Size. So numerical value or the size represents the magnitude. So in this example, 2 blocks would be the magnitude. Now the direction has to be a physical direction, right? Physical direction, such as um, the four cardinal points, right? Right, north, south, east, and west, right? Like never eat soggy waffles, right? Or it could be like up, down, right? Left, right, right? You could simply say positive or negative x-axis, right? Or positive or negative y-axis, and positive, negative z-axis even, right? So, so physical direction is very, very necessary. Okay. However, scalar quantity only has magnitude, right? It has no direction. So there's so many more scalar quantities than vector quantities, right? For seniors who are taking physics at Conestoga, if you just remember or memorize these vectors that I give you, right? Then anything else, if it doesn't get included in that, the chances are it's going to be a scalar quantity. All right. So vectors are going to be represented as a little tiny arrow on top of a variable or a letter. Okay. This tiny little half arrow that you see on top of a variable means it's a vector. In your textbook, your vector is written as a bold-faced letter, but it's kind of hard to write bold-faced letter every time you write as a vector. So they symbolize vector with this little tiny arrow on top. It's only half an arrow, really. Okay. Scalar, however, has no arrows, not boldface, it's a regular face. Okay? And later on, we're going to talk about this funny looking xhat. So this is red, okay? Xhat. This right here is hat. And this is actually a mathematical term. So it's not something that I'm making up. All right? In Europe, instead of saying hats, they will say roof. Right? So this would be X roof, right? Y roof. In the United States, we call it X hat, Y hat, Z hat. That symbolizes a unit vector. Most of you know like unit circle, right? Back in the pre-calculus or math analysis, right? The pre-calculus time when you were learning the unit circle, it was a circle with radius of 1, and that was the unit circle, right? So unit vector has magnitude of, right? Guess what? Magnitude of 1. Yeah. And it will always point along an axis, such as x-axis, y-axis, or z-axis. If it points along the x-axis, we call it an x-hat. If it points along the y-axis, we call it y-hat. When it points along the z-axis, we call it the z-hat. All right? So here are 8 vectors that you need to memorize and know. So if you know these 8 vectors, and if it's not one of them, most likely it's going to be a scalar. For juniors, there's going to be 3 more, maybe even 4 more vectors beyond this. But for seniors and for the rest of the you this year physics, this is all you need to know. So first vector we should be familiar with is a position vector. Now position vector can be represented as x, y, z vector, sometimes r vector, right? If it's more than one dimension. Right? So sometimes the position vectors can be represented as a function of time. So your position changes depending on what time it is. And similarly, y is a function of time, etc. So vectors can be represented as a function of time. Okay? Sometimes your three-dimensional vectors can be represented as a function of time with, right, like x, y, z function. And these can also be function within the function. Okay? Parametric equation. The second vector that we should be familiar with is displacement vector. Now, displacement vector is basically change in position vector, okay? Change in position. So, change in position along the x-axis is known as the displacement in x, or your x final position minus the x initial position. Okay? Or if it's more than one dimension, then your delta r, or change in position, is basically rf minus ri. Okay? Then the third one is the velocity vector. And the velocity vector is simply change in position. Change in x over change in time. Okay? Now the velocity vector can also be a function of time. Okay? For those of you who are taking calculus, your velocity vector is the derivative of a position vector. All right? And fourth is the change in velocity vector, and that's kind of obvious, right? And change in velocity vector is simply just delta v, right? Which is vf minus vi. Okay? Fifth is acceleration vector.
I can't read what velocity vector is supposed to say.
This right here,
Yeah.
this is delta x over delta t. Yeah, I write it bigger here. Is that better?
Yeah.
All right. That can also be a function of time as well, velocity vector. And this velocity vector is actually the first derivative of the position vector. Now for the acceleration vector, is a, and that is the change in velocity over change in time. And that can also be as a function of time as well. And as we all know, acceleration vector is the derivative of that velocity vector, right, function. Then, number 6, we have force vector, okay. Now, force vector is F, and that is equal to mass times the acceleration vector. And number 7 is momentum. And that is represented with lowercase p, and that is m times the velocity vector. And last but not least, but here, impulse can also be two different forms. An impulse vector is represented with capital J, and that is the change in momentum vector, or force vector times time. Now, for juniors, if you're staying around after the seniors leave for their senior vacation, we're going to be learning about rotations. And when we do rotations, we're going to be talking about torque, which is a rotational force, and then rotational angular momentum, as well as angular impulse, and so on. So there could be like 3 more, vectors beyond that. But for now, if you know these 8, once you know these 8, and if it's not one of these 8, then it has to be scalar quantity. All right? So you just memorize the 8 and you're fine. Okay? All right. So vectors now can be represented graphically using arrows. Okay? So if you were to represent a vector as using arrows, since it has magnitude and direction, I hear music, Dana. All right. Thank you. So if you take a look at uh, uh, the length of an arrow represents a magnitude. So if I have a vector represented graphically, then the length of an arrow represents the magnitude, right? So the length is the magnitude. If huge magnitude, longer the length, right? Magnitude again means numerical value of the vector, right? Then there are two other things that are involved. Here, this arrowhead represents the direction. So we could call that head of a vector, or sometimes the tip of a vector, okay? The head of the arrow or the tip of the vector will always point in the direction of the vector. The other part is the other side of the head, and that is the tail of the vector, okay? The tail of the vector obviously is at the end of the vector where it terminates, right? So if we were to actually represent a vector graphically, let's say I have my vector A, which is 3 meters long in the positive x direction, okay? So this vector A is read as follows: positive 3 meters x hat, and that is 3 meters of length in the positive x direction, okay? So to represent that graphically, you obviously you're not going to be drawing 3 meters on this paper, so you have to scale it down, right? Saying, you know, 1 centimeter is equal to 1 meter, and then you draw 3 centimeters to represent that 3 meters, and you draw it along the x-axis. You place the arrow or the head of the vector in the direction of the positive x-axis direction, right? And your tail can start from the origin, 0. Okay? Now, if I were to move this A vector, let's say like 2 over this way, and let's say it starts at positive 2 meters in the x-axis. As long as it goes 3 meters from there and end up at 5, it's still same A vector. Matter of fact, I could take this out and put it away from the x-axis as long as it's pointing along parallel with the x-axis and is 3 meters long and is pointing in the positive x direction. It's the exact same A vector. Right? That's why it's very useful to use vectors. Okay. Now, let's say I represent another vector, vector B, and this time my vector B is 4 meters long, pointing in the negative x direction. Again, I could start my vector from my origin and then point in the negative x direction 4 centimeters to represent my 4 meters. Okay? So the positions have distance, right, which is the magnitude from the origin, and they have direction from the origin as well. That's because we drew it from the origin. I mean, it makes sense to draw from the origin because if you have a stopwatch, you should always start from 0, instead of like 4.2 or something. All right? Just defeats the purpose if you don't start from 0. All right, any questions? All right, so these vectors now can be added. So if we were to add vectors graphically, here, let's say I add a vector plus the b vector. When I add two vectors, I get a whole new vector c, which we call that a resultant vector. The resultant vector is another vector that's pretty much born out of adding these two vectors. Okay? So the C vector, it doesn't always have to be C. It could be like R, or it could be T, or it doesn't matter, right? It doesn't always have to be two vectors either. It could have multiple vectors can be added, right? It's called the resultant vector of the vector addition. All right. So let's say I'm taking a look at these two vectors that we already saw on the previous page. Here's my vector A. I'm going to represent that vector A with my aquamarine blue. And it is 3 meters long in the positive x direction. So I drew that out. And I'm going to represent my vector B with my passionate purple color. And that is 4 meters long, right, in the negative x direction. All right. So if I were to add this graphically, A plus B, first place the A vector on a different x-axis, right, starting from the origin. So pluck out this A vector and then put it right onto a new axis. So let's draw, right, A vector from my origin. I'm going to draw 3 meters along the positive x direction. All right, so it's kind of hard to see because I drew it right over the axis. So maybe I could put it down slightly down so you guys can see the colors better. All right, so here's my A vector. Then I place the tail of a tail of B to the head of my A. So if I pluck out the B and then place the tail to the head of my A and draw it out. So place this tail part and then place it to the head, right? So it's going to look like if I place my tail onto the head of A, it's going to look something like this. Now, obviously, they're going to be on top of each other, but I drew it so that it's slightly off so you could see the colors better. Right? Doesn't make a difference. So here is my B vector. So when I add them up, my resultant C goes from the tail of A to the head of the last vector that I'm adding. So this is my vector C, which is the resultant. From the origin to the head of my... Now notice I'm putting these arrowheads down. If I don't have these arrowheads, they're not vectors. If I just draw a line without the arrowheads, that means it is not a vector. So I will take points off if you don't draw the arrowheads down. So here, my vector C, which is the resultant, happens to be negative 1 meter x hat as my resultant vector C. Are we okay with that? All right. Well, let's say these vectors are so big, like instead of these 3 meters and 4 meters, let's say they're like 150 meters and 25 meters and so on. I mean, that's just but I'm not going to be drawing all this thing out in the huge, graph paper. So we could actually add these vectors graphically. So let's say my vector A happens to be 150 meters x hat. I have to really look at these x hats They better be same. If they're not same, we cannot just add them by looking at numbers. If these are same, then yes, we just treat them just like if we're adding just regular algebra, numerical numbers. So when we add this, first thing is always check the unit vectors. If they're the same, just add the numbers, or in this case, we're adding the negative. So my C vector becomes just positive 125 meters x hat. All right, so that was easy because my x hat and my y hat were the same. All right, so again, here's 125 meters x hat. If they're not the same, we're in trouble. Okay. Here again, I have a vector being positive 573.5 meters y hat. That means this is along the y-axis. And my b vector happens to be negative 43.25 meters y hat. So again, these are same. So now we can actually add them like a regular number. All right. So if I add them up, this is negative. So I'm adding the negatives. Same thing as subtracting. So the positive 530.25 meters y hat. So that's easy enough, right? Okay. Well, if I can add vectors, that means I should be able to subtract vectors, right? But subtracting vectors is the same thing as adding vectors that are negative. But if you could like change the vector into a negative vector, then all you need to know is how to just add vectors, right? Because you're adding the negative vector. So to give an example, how do you negative it? Well, you can negative it by putting a negative sign in front of it. So here, let's say I have a vector b. Let's say this is my vector b. Notice it's about 3 centimeters long, right? 3 centimeters long, and it's pointing in this direction. And I don't know exact direction what that is. I don't even know what angle that is. So I just know it's pointing in that direction. Now, if I want to negative this, all I have to do is draw exact same length, same magnitude, which is 3 units long. Notice how they're parallel. Now, if I place the arrowhead on the other side, now it became negative b vector. Okay, see how the arrowheads are very important? Okay, well, I'm going to go even further. If I actually draw another vector that is twice as long as my b vector, pointing in the opposite direction of my b vector, then this is negative 2b vector. All right? So now that I know how to negative it, you should be able to subtract vectors using just addition property. Right? So a vector minus b vector is equal to c vector is exactly the same as a vector plus the negative b vector is equal to c. Okay? Boom. Right? So for example, if I were to do this graphically, let's make all these centimeters. Okay, just to make it easy for everybody. Centimeters. I want to do a minus b vector. So I know my b vector is going this way, like negative 7 meters going this way, right? So this is my direction of my b vector, right? Negative b vector would be negative of negative 7 centimeters x hat. So it should actually go this way 7 meters. right? 7 centimeters going this way. That's my negative b vector. So since a minus b is exactly same as a plus, right, negative b vector, we can say, let's draw the a vector first, which is 4 centimeters in the positive x direction. So here is my a vector. So here's my a vector. And I'm going to add my negative b vector, which is 7 centimeters in the positive x direction. So here is my negative b vector. Therefore, my resultant vector will start from the tail of my first vector, which is a, and it will connect to the head of my last vector that I'm adding, which is tip of my b, or tip of my negative b, I should say. So that's my c vector. So when I do a minus b, that's same thing as positive 4 centimeters x hat minus negative 7 meters x hat. So I get positive 11 meters or centimeters x hat. Well, if that's true, this green line should be exactly 11 centimeters, right? So let's measure it. Yeah, look at that. Booyah. 11 centimeters. Cool. Alrighty then. Let me see if you guys can work on pages 5 and 6. And I'll give you next, I don't know, 15 minutes. See if you can work on it. So here, for lesson 1 problems, vector in 1 dimension, I will keep that color convention going. So 1 centimeter is equal to 1 unit. So we have 4 units in the positive x direction for a vector. And I'm going to keep the a vector as in aquamarine blue. And my b vector is 7 units. In the xhat direction, I'm going to keep that as passionate purple. And my c vector resultant will be environmental friendly green. All right. So let's draw the a vector first. And a vector says 4 units, which should be represented as 4 centimeters long. So here I will draw my 4 centimeters from my origin in the positive x direction. So here is my a vector. Okay, make sure you draw the arrowheads down. So a vector is that. Then I will add my b vector, which is 7 units in the negative x direction. So here I will draw 7 units from the tip of my A to the negative x direction, like so. And then this is my, now I drew it slightly off so you could see the colors better, but they should be right on top of each other, okay? So here's my B vector. So my C vector is from the tail of A to the tip of my B, and that is my resultant vector C, and that is that. Therefore, if I were to measure this, this looks like 3 centimeters, right? So C vector is equal to 3 centimeters, but going in the negative x direction. Boom. So that's my number one. So the second one, here I have my A vector as negative 5 centimeters x hat. So I'm going in negative x direction for 5 centimeters. So this is my A vector right here. So here's my A. And my B vector is positive 9. Therefore, I'm adding B vector to my A. So at tip of my A, I will place my tail of B. So here is my B vector, 9 centimeters long in the positive x direction. So here's my B vector. So my C vector is from the tail of A to the tip of my B, and that is positive 4 centimeters. X hat. Boom. And now let's take a look at another one. Here I have positive 5 meters or centimeters x hat. So here's my x. And here's my A. Then boom. So here's my A vector. And I will add 3.5 centimeters on top of my A. So the tail of my B should be a tip of my A. And I should go 3.5 in the positive x direction. So here's my B. So my resultant C is from the tail of A to the tip of B, which happens to be this, and that's 8.5 centimeters, which makes sense, right? So here's my C. So my C vector is positive 8.5 centimeters. Excellent. Alrighty. Now let's take a look at page 6. Now we're going to subtract, right? Again, I'm going to keep the same color scheme where my A is going to be the aquamarine blue, my B is going to be my passionate purple, and C is going to be environmental friendly green. So this is exactly same as saying, right, A plus, right, negative B vector, right? So first, let's draw out 5 centimeters in the positive x direction. Alright, so we'll do that first. So here's my A vector. And my B vector is going to be 8, but I'm going to add negative B, so it's negative 8 from the tip of my A to the negative x direction, like so. So this is my negative B vector. Therefore, here's my C. My C becomes just 3 centimeters in the negative x direction. Okay, so my C vector is equal to negative 3 centimeters x. And my A vector here is negative 4.5. So let's draw that. So here's my A vector. And my B vector, I'm going to add negative 6. Therefore, it's going to continuously go in the negative direction, like so. So here is my negative b, which I'm adding. So my resultant vector is 10.5 centimeters in the negative x direction. So here is my c vector. My c vector happens to be negative 10.5 centimeters xhat. All right. Last one. My a vector is equal to negative 5.5. It's my a vector. My b vector is going to be negative 10, so I'm adding the negative b, so it becomes positive 10 from the tip of my a, like so. So here is my negative b vector. So when I add the negative b onto my a, I get my c vector, and my c vector here is positive 4.5 xhat. All right.